Hello, this is the Mr. Da Maths channel. In this multi-part series of videos, I'm going to be breaking down what 3D vectors are and what's expected of you in the WJEC spec to work with in terms of these 3D vectors. Crucially, in this video, what I'm going to go through is the structures that you should be working with and you should be very confident with doing calculations with, because ultimately these two structures are what define most of your 3D vectors work at AS level. So, the first thing I want to talk about is the equation of a line in 3D. And visually, this is very simple to kind of imagine. Even in 3D space, you can just have your origin again at some point in this 3D space. This sort of diagram I really like, because ultimately the only real reference point that you need is the origin. It doesn't really matter which way the axes are orientated, because ultimately that doesn't change the nature of what your object is. It's still a line at the end of the day. So you could just draw some arbitrary line that is maybe in this 3D space over here. Crucially, what you would do if it was a 2D space was you'd check what the change in y over change in x was, i.e. the gradient. But that becomes a little bit messy in 3D, because now you're working with three variables. Now you have to consider what the change in x and y is, the change in y and z is, the change in x and z is. So ultimately the increase in dimension causes an added complexity to the amount of changes that we have to look at. Therefore, we ditch the idea of changing one variable and changing another variable completely. What we consider instead is what direction is this line moving in, and do I know a starting point from where this line can, start from? i.e., a line in 3D is defined by a starting position vector, and all of these will be defined from origin vectors. So let's call this starting point A. Then the position vector to A will be little a. And I know of another point that's present on this line, which is B. And I'm going to call the position vector to this line little b. Now, if I call this line L, there's a very elegant way in which I can define this line. It's, first of all, the direction in which this line is headed. So clearly, if I were to draw A and B, if I start from A, then the line is headed towards B, and so on and so forth, off to some value, infinity even. So, basically, what I'm trying to get at over here is that as long as I know the starting point, which is my position vector A, I can keep adding on some multiple of the direction vector, which is going to be this way. Now, how do we think about what this direction vector actually is? How do we go about trying to work out what this direction vector is? And the nice thing about that is, if you were to just apply your rules of vectors that you learned in your previous video, which I told you to be very comfortable with, we can just see that the same line or the same vector that passes through A and B will represent the direction of line L, because A and B are on the line L, okay? It doesn't matter what these points A and B are, they aren't really special. I could choose them to be anything as long as they're on this line. Therefore, I can use these two points, I can work out what the direction vector is, which is going to be AB. So the vector AB will be my direction. But in this form, I can't really work with it. This isn't exactly a sort of thing you can just look at and calculate what the actual value, the numerical value of the direction vector is. What you can do instead is you can look at your origin vectors again, which is why I was trying to iterate origin vectors are very important over here as an idea. Clearly, the vector from A to B is the direction vector. We can say that with absolute certainty. AB, however, can also be written as, if you were to take a separate path from A to B, like from the origin, then clearly you'd be going against the flow of A as an origin vector and with the flow of B. So that's another way in which I can get to B, which represents exactly the same vector. It kind of enforces the same idea as no matter what path you take, if you end up at the same point as you did before, the vector, your travel, is going to be the same. So another way in which I can write AB is B minus A. Therefore, my line L can be defined as R, the position at which I'm at along the line. So I could call this like R over here if I'm at some position, and I can call the origin vector to that position little r. Then the origin vector, or the origin vector for my position R, is going to be equal to this: my starting point plus some constant lambda times my direction, which is going to be some other origin vector, minus A. Should be very consistent with my notation, so I'm just going to use underlined from now on. So what I'm trying to get at over here is that with this line right here, what you really only need is 2 points to work it out. If you know that there's 2 points present on this line, then you can work out the equation of the line. And this is the vector form. Essentially, what I'm trying to say over here is that if you have a starting position and a direction, that's it. That's your line. And crucially, this lambda can be any value which is real. Therefore, if I multiply this direction vector by maybe a half, I can be over here. If I can multiply this direction vector by pi, I would be somewhere down here. So yeah, essentially this is what defines your line. And this is going to be your parameter, which is going to tell you where you land on your line. You can obviously expand this idea a bit more. You can say that A has 3 components, so I'm going to name them AX, AY, and AZ. And then plus lambda, and now I'm going to switch to my direction vector. So my B minus A becomes my direction, which it is. So my direction vector will also have 3 components: dx, dy, and dz. From this, you can quite easily work out what the Cartesian equation of a, or I shouldn't be saying Cartesian, but the XYZ form of a 3D line. So if you, and I'll leave this as an exercise, the Cartesian form of this line will just be x minus ax divided by dx, which equals y minus ay divided by dy, equals z minus az divided by az, or dz, sorry. And that is your line. And clearly we can see sort of like a relationship over here again. Here we have dx, dy, dz as the components of our direction vectors. So really it's just considering one plane of movement at a time and seeing where it equals another plane. And that is what gives you your line. So in a way, if you have a very strong intuitive sense of how 3D vectors work, then you can just look at this and figure out that this should be the equation of the line if you use x, y, and z. So yeah, that covers the equation of a line in 3D. Obviously, these ideas, and I have mentioned this before, I think, these ideas can also be scaled down into 2D. So with all of this notation right here that I've written down with vectors and starting positions, you can use that in 2D as well if you really want to. However, we rely more on coordinate geometry and such with 2D, especially in normal maths. Although, of course, if you like this notation a little bit more, then you can't be faulted for using it, essentially. It's pretty elegant in its own right. Another structure that you need to be very well aware of is a plane. So, a plane in itself is also a pretty simple structure in 3D. You're just going to have some infinitely extending I'd guess in this sort of representation, a rectangle that would extend outwards like this. And yeah, still pretty easy to visualize in your head over here. So a plane can just be defined as maybe somewhere X and Y and Z are related in some sort of way, but that's a very like ambiguous way of thinking about it. What we want in mathematics is for our ideas, for our concepts to be extremely rigorous. So let's try and think about how we may define a something like a plane. And there's a lot of ideas that you need to be introduced to before defining a plane. And we'll go through what those are as we try and work out what the equation of a plane are. I feel like if we go through with that sort of structure, then it's much easier to learn the place of these operations, is what I'm going to call them, in 3D vectors. All right. So what you need for a line to be properly defined is 2 points. And you need to know where the origin is as well. For a plane, if you were to just intuitively think about it, you need 3 points. Or rather, you need 2 points and a normal to the plane. So if you were to arbitrarily choose two almost like line segments on the plane, and the normal to that plane, or yeah, the normal to those two vectors right there is this vector right here, then it won't matter what I choose as my points, because I could choose one of these points to be all the way out here somewhere, provided it's still on the plane. But what I need is a normal vector and 3 points which are on the plane. Sorry, let me reiterate. You need 3 points on the plane to start with so that you can work out what the normal vector is. What you get, if you were to, again, kind of work through this in your own time, is R, this weird symbol right here, equals A, this symbol, weird symbol right here. What I've done here is I've defined some points without telling you. So you could say that clearly the n over here is going to be the normal. R is just going to be some point again. So the point or the origin vector to that point is going to be little r. And there's going to be another arbitrary point A, of which the origin vector to that point will be little a. If you work through this in your own time, what you would get is n dot r minus a, which equals 0. And the way I get this is by using dot product, which is this symbol over here, this dot that I've written. Crucially, what the dot product is it tells you what the angle between two vectors is. Two n-dimensional vectors. Or more, I guess, a little bit more broadly, a dot product essentially tells you how much one vector is in the same direction as another vector. So, if you have a vector that goes maybe like this, and like this, and crucially, it doesn't matter where these vectors are, I've only joined them at one point of origin because ultimately it's a little bit easier to see the relationship that way. And I have this vector, let's call it x, and then another vector y. Then what your dot product tells you, or what your dot product tells you, is that x dot y is equal to the norm of x, which is just you using Pythagoras, times the norm of y times cos of the angle between them. This is a formula that is very useful to remember, especially later on when we're going to look at how lines and planes behave together and what you can calculate from them and what you should expect in terms of questions in your exam. But this is a very important formula right here. Okay, so the dot product of x and y as vectors will be equal to the norm of x times the norm of y times the cos of the angle between them. Obviously, there's a simple, for someone who studied ahead of the course, obviously, which may be some of you watching the video, but a much simpler way of calculating x dot y is if you know the components of x and y. So let's say x is maybe 2, 3, 1, and then you dot it with another vector, so you know the components of y, which are going to be maybe 3, 1, 4. Then I can see by observation that it's just going to be 3 times 2 plus 3 times 1 plus 4 times 1, which is going to be 3 times 2, 6, plus 3 plus 4, which is just going to be 13. So that gives you the dot product. Ultimately, if you don't know the components of the vectors given to you, but you know their magnitudes and your angle, then you can work out dot product that way. But yeah, another thing that you could do is work out the angle between two vectors if you know what their components are. So if you just do a little bit of rearrangement on this, then you get this. So now, if you know what the components of the vector are, you can actually just dot product it using this method right here, and then you can just work out what the norms of x and y are, and then apply your arc cos to get your theta, your principal angle. So yeah, that is dot product. Crucially, if you consider what the dot product of two vectors that are normal to each other are, then you get cos theta equals 0, because here, if I'm talking about the normal of two vectors, or if I have two vectors that are normal to one another, so like this, so suppose I take x and y again, if I have two vectors that are normal to one another, then the angle between them obviously is going to be 90 degrees. But from your normal trigonometry, you should know that cos 90 is 0. Ultimately, what you get is x dot y over the norms of x and y equals 0. Multiply both sides by the norms of x and y, you get x dot y equals 0. So if x and y are perpendicular to one another, then the dot product of x and y will always be 0. I've used that idea over here by considering my vectors right here. So this vector right here, a to r, is just going to be r minus a. Of course, if you're really fluent with this sort of notation, then you can just work it out based on what you can imagine in your head. So I really highly recommend that you stay extremely strong on this topic, because it requires you to be very, very precise. As with any other topic, obviously, in further maths, but especially further vectors. Clearly, what I can see is that if I dot the normal with r minus a, then it's like me dotting the perpendicular with a vector. So the perpendicular of a vector, dot with the vector itself, is 0, clearly. The nice thing about this is that, as with multiplication, I can expand this bracket as well. I can say r dot n minus a dot n equals 0. And then rearranging, you get r dot n equals a dot n. That's why you need at least 2 points and a normal vector to the plane to define it, because the 2 points over here are arbitrary. You can choose those points to be any point as long as they're on the plane. The normal is not arbitrary, however, because whichever direction the normal is pointing at, whatever the arbitrary vector is that is normal to that normal, perpendicular to that normal, is going to be part of that plane. And since you can choose that vector to be anything, you can kind of infer from that that whatever real vector that you choose, or a vector with a real entry that you choose, that is on that plane, is going to have a dot product of 0 with that normal. Ultimately, what you get out of this sort of thinking with this logic is that I can work out the equation of a plane, at least in vector form for now. This out here is trivial, because ultimately what is written over here is just a constant, because a we know and n we know. And just as always, I've represented r as my position. So r, in fact, could be anywhere over here, basically just where I want to walk to on the plane. You can think about it that way. But this over here is just a constant. I could call this constant d if I like. Have I used d anywhere? No. Okay, so here I could just say r times n, or r dot n, will just be equal to some constant d. This is a very useful form right here. You can kind of work with this form in basically any sort of way that you like, and frankly I think this is quite an elegant form in which you can represent a otherwise quite foreign topic to you. So in essence, compared to anything in further maths, this is actually like really simple, isn't it? It's just three, I guess 2 vectors and a constant. So yeah, there's not really much to remember over here except maybe geometric interpretation, which some of you may not like. This is why 3D vectors is sort of like a hit or miss topic. Either you hate it or you like it. What you do know about this normal vector is its components. Otherwise, you won't be able to work out what this plane is. A normal is key for you to work out what the plane is, as is maybe another point that is on the plane. Or maybe 2 of the points that's on the plane, I should say. But yeah, this normal I could just write as equal to maybe nx, ny, and nz. So I've just represented what my components are here. Rather, I'm going to use 1, 2, and 3 because later on it will kind of become a little bit, it'll look like clutter if I expand all this out. So r is just my position. So r could be any general point, x, y, z. So if I'm talking about my position over here, clearly this is going to be on the plane, isn't it? So if I substitute these ideas, or what I've done over here is these deductions, into the relationship that I found, then I get n1x plus n2y plus n3z equals d. And this is the Cartesian form for a plane. Ultimately, what is really complicated about all this stuff that I've taught you over here is that oftentimes it's much easier if you know the derivation for it. Otherwise, everything in 3D vectors may seem a little bit wishy-washy and kind of uncalled for. Maybe all these formulas coming out of nowhere makes your head hurt a little bit. But if you know the derivation for all this, if you are strong enough with your geometric interpretation, then this entire topic kind of boils down into one thing. If I have a vector and well, if I have a position, okay, and I have a direction in which I want to go on some object, then I just have to use the form that I have for that object and just work through what that is so that I can find my position. So in that regard, this is a very reductionist sort of way of thinking about 3D vectors, but it is essentially that. It's just thinking about what your position is and what, I guess, 3D object that you're working with. But yeah, you're only going to be expected to work with planes, points, and lines in 3D. In the next video, I'll go through what the relationships between these sort of 3D objects entail. So, what you could possibly be asked to do with these sort of relationships, and ultimately what you need to calculate as well. Oftentimes, these questions are worth quite a bit of marks as well. So these sort of relationship questions, which I call them, they can be anywhere between 5 marks to 8 marks. So they're worth quite a bit if they come up on the exam. Especially one question which I really want to kind of give a prequel to right now is if I'm given 3 points which I know are on the plane. So this. Then can I work out the equation of that plane? The Cartesian equation, let's say. And that is one very interesting question that you could ask. Obviously because, I mean, think about it kind of geometrically. If you have 3 points, then you can always draw a plane so that the plane goes through all 3 of those points. So yeah, in itself, that question is pretty large on its own. I think it was asked in the 2022 further pure paper in WJEC. That on its own was 8 marks. So if you'd really like to give that question a sort of go with the knowledge that you have right now, because now you have all the prerequisites with the normal vectors that we covered in the previous video and the structures that we covered in this video. So if you really want to, then you can kind of look through that question. You can figure out what the answer is for yourself, which obviously, as someone teaching maths on YouTube, I recommend you do. But I'll conclude at that. Thank you for watching as always.